Hi guys, welcome to KK Chemistry. My name is Dr. Hussainullah. Today we will be discussing lecture number 27 of Inorganic Electronic Spectroscopy. Okay, the topic of our discussion is group theory and its application in chemistry. This topic will be covered under the following outlines that are: what is group theory, element of symmetry, and the last one is application of a group theory. So, what do we mean by group theory? Here, as you can see, group theory is simply the study of symmetry and its application to gain information about the physical property of an object. You can say a molecule if we are dealing with the chemistry. Okay, but apart from here, we can also say that group theory is a combination of two words, group and theory. Group means collection of elements, and here by element we means like inversion center, improper axis of rotation, principal axis, plane of symmetry, identity. And plane of symmetry we will be dealing with vertical plane, horizontal plane, and dihedral plane. And by theory we mean any idea that explains some activities. Over here by activity we mean the application of symmetry elements. Collectively we can say that group theory is nothing but application of symmetry to explain an object. Here in chemistry we will be talking about a molecule. Now you know Taj Mahal, one of the beautiful piece of art. Why it is so famous? Why it is called a beautiful piece of art? It is because it looked like the same when it is bisect, or in other words, when we apply some symmetry operation, it fulfills all the requirements that are needed for a beautiful object. Okay, but here in chemistry we'll be talking about a molecule. The symmetry elements, as you can see, are these one as discussed earlier. The main symmetry elements are principal axis, improper axis of rotation, inversion center, identity, and plane of symmetry. Well, actually group theory also, you can say, quantify a beauty with the help of symmetry elements. Now we come to symmetry. So what is symmetry? Actually, symmetry is the name of invariance. What is invariance? Invariance means if we bisect an object into equal halves and each part is a mirror image of the other, each part is a mirror image of each other, so we can say that no change has taken place. Basically it is derived from the Greek word symmetry, which means to mirror. Now what to mirror? Equality, symmetry, no change in a property, no change in shape, no change when we bisect a molecule or any object, and both sides are mirror images of each other. Here you can see it is symmetry means invariance and is a fascinating phenomenon in nature. So you can say symmetry is nothing but the application of symmetry elements, or you can say that symmetry is worthless without applying symmetry operation, or simply by applying symmetry elements we can talk about a specific property of an object. These symmetry elements are identity, proper rotation, axis, plane of symmetry, center of symmetry, inversion center. Center of symmetry is also called inversion center. Improper axis of rotation. Improper axis of rotation is also called improper rotation reflection axis. When these elements combine, it creates a group. So by applying these symmetry elements on a molecule, it is called a symmetry operation. Actually, what is symmetry elements? By symmetry elements we mean any point, space, or plane through which symmetry operations are applied. You can see Taj Mahal. If the Taj Mahal is bisect to two equal holes, the right one is a mirror image of the left one. That is why it is called a beautiful piece of art because it is symmetrically designed, and each side forming a mirror image when a line is passed through its center. Now, we can also apply symmetry to some facial objects, some images. Look at the first face, first image over here. If a line is drawn which passes through its forehead and nose, you can see the left hand side of his face is not a mirror image of the right hand side of his face. Means left hand side is not equal to the right hand side and the face is unsymmetrical. Look at the second image. When a line is passed that equally divide his face, you can see the left hand side of his face is a mirror image. The right hand side of his face mean left side is equivalent to the right side. So this face is more symmetrical as compared to the first one. Now you will be thinking about which one is the most beautiful. Okay, the image second one is more beautiful as compared to the image first. And Allah says in the Holy Quran, لَقَدْ خَلَقْنَا الْإِنسَانَ فِي أَحْسَنِ تَقْوِيمٍ. Allah says, we have indeed created man in the best of molds. Okay, now look at this beautiful kid. The picture on the left hand side has a mirror image on his right hand side. So it can better explain symmetry. Okay, so by this picture we can say that symmetry is a name of invariance to transformation. In other words, we can define symmetry as an art to quantify a beauty. Now each symmetry elements will be explained in detail. Here first one is the identity. Well, by identity we mean operation which leave molecule unchanged. What does it mean? Suppose you apply a symmetry element and you observe no change in the molecule. We can say this symmetry operation has taken place and that particular object. We can also rightly call identity is an art of doing nothing. Look at these two molecules. Okay, structure 1, you can say look like the same as structure 2nd. So what do I mean by this? It simply means we have done nothing to the structure, and these two structures are superimposable. Okay, so that's why we say that symmetry identity is an art of doing nothing. It means it just like you have done nothing with the object, you have not applied any operation. So identity exists in every molecule. Sometimes we can get an identical structure by applying more than one operation. We will discuss it later on. Okay, means suppose if you apply C2 on this object, this will shift over here and this will shift over here. Then apply sigma V, a mirror plane, vertical mirror plane. You will get the same structure. That is why we have used over here a sentence that we can also get an identical structure by applying more than one symmetry operation. Look at this molecule again. Here in structure 1, water molecule possesses 2 hydrogen atoms. F means that both of these hydrogen are toward us. You can just see their fronts. If a C to 1 operation is applied on it, mean 180-degree rotation, we get an equivalent structure where the back of both hydrogens are towards us. Okay, these two structures are not identical. Why? Here is back, here is front. So these are called equivalent. Why equivalent? Because here are hydrogens and here are also two hydrogens. So oxygen and oxygen mean equivalent. But if we rotate this orientation second by 180-degree, we get another orientation where the front of both hydrogens are towards us. Now you can compare structure 1 and third one. Both are identical. Both are superimposable. You cannot distinguish structure 1 from structure 3rd. Okay, structure first cannot be distinguished from structure 3rd, but you can distinguish structure first from structure 2nd, and also structure 2nd from structure 3rd. So symmetry operations are applied till we get an identical structure. Here E mean 180 plus 180 means 360-degree, and 360-degree is equal to C22 means we have applied 2 times. This 2 means 2 times 180 rotation. So it will cancel out. We will get 1, and this one is equal to identity. Got it? Hope it is crystal clear to you. Here another example of water molecule. We are dealing here with identity. The other symmetry elements will be discussed stepwise. As you can see, identity means that hydrogen labels with same number came back to its original shape after twice C2 operation. Okay, then we get an identical structure. These labels are nothing but just to differentiate one hydrogen from other. so that if we apply C2 operation, then we can notice the difference between first structure or first orientation and the second one. Okay, like here we can see that these two orientations are non-equivalent. These are not equivalent. Why? Because here hydrogen, here like deuterium, if we perform C2 operation by 180, okay, we get deuterium on our left side and hydrogen on our right side. These two structures are not superimposable because here deuteriums and here are hydrogens, so we cannot superimpose these two structures, means these are not identical as well as non-equivalent. Come towards here, apply C2 operation, we get hydrogen, 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 hydrogen. Just forget the numbering, the labeling. So you can superimpose this one if we remove the numbering, but we have just number it to see the change. Okay, by C2 one operation, the red hydrogen labeled 2 is towards our left side and the other one H1 is toward our right side. Where in structure first H2 hydrogen is towards our right side and H1 is towards our left side. Though in this case these two cannot be superimposed. Why? If you superimpose this orientation over this here will be H2, here is H1, so not identical, but we call it equivalent. Why? Here hydrogen is hydrogen, here is hydrogen, here is hydrogen, here is hydrogen. These numbers are just to show that some symmetry operation has taken place. Again, apply C2 operation on this molecule. If we apply C2 operation on this molecule, it will become C22. C21 is here. 1 mean first rotation through C2 80 degree. C2 mean second rotation through 180 degree, means two rotations. We have rotated the molecule twice, so again we get an identical structure, just like the first one. Now these two are superimposable on each other and are identical. So what we have told you over here, that identical means that the same hydrogen came back to their original position. So identity exists in these molecular structures if we rotate this molecule by actually a 360 degree. Okay, will mean that hydrogen atom are still there after rotation. We have just labeled it for simplicity and understanding. Now again, in this case, the hydrogen are same, whereas in this case, hydrogen are different. Now, if we apply C2 operation, we get the same molecule, the same orientation, means both of these structures are identical. Here in this case, if we apply C2 operation, we get a different orientation. These two structures are neither identical nor equivalent. So we can say that in this molecule C2 operation, do not exist and C2 is not a valid symmetry operation. There are some molecules, as I have shared with you earlier, that identity exists in every molecule and every object. If there is no identity, it means nothing exists. Okay, so this molecule, you can see all the atoms are labeled differently. Okay, suppose if you rotate it by C2, you do not get the exact structure is the first one. So C2 one operation do not exist over here, etc. So this orientation only possess identity. Okay, principal axis. Well, by principal axis we mean an axis of highest order of rotation. So if we apply a principal axis on a molecule, like by principal axis I mean C2, C3, C4, anyone. If the molecule remain the same, then we call that principal axis exists in that particular molecule. And if by rotating a molecule, or you can see while rotating a molecule, if we get the exact structure, means symmetry exists. So prove that principal axis is also a symmetric element. Remember, principal axis is also defined as a z-axis, mean it is also taken along the z-axis. In the next slide, we will be doing with some molecule. If we apply a C2 operation, it gives orientation B, which is n distinct from the original structure. Again, water molecule. Don't feel boring. We are using water molecule because it is the simplest one. Okay, so if we rotate molecule A by 180, we get B. Now here we have not labeled it as 1, 2, hydrogen 1, hydrogen 2. Okay, just to show you that C2 one operation exists in water molecule. Well, after rotating the molecule through 180, we get this one. So both are mirror images of each other, or you can say both are superimposable. So we have performed a two-fold operation. 180. Okay, here you can see Cn over m. Cn means rotation, m means how many. In water molecule, C2 means 180, 1 means once. Okay, so this symbol, you can say this representation is used for this purpose. Now question might be in your mind, how can you differentiate between two axes there? Which one will be the principal axis and which one will be not a principal axis? Okay, Again, water molecule. I think it's too boring for you, but keep patience. Okay, here by this slide, what I mean actually. Well, here we can summarize the principal axis. Now you can see this circle. If we rotate a molecule by 90, we call it C1. If we rotate a molecule by 180, we call it C2-1. If a molecule is rotated by 360, we call it C2-2. Means C2-1 here. C2-2 means 2 times 180 degree rotation has been performed. Okay, so this is the same thing as previously discussed. Here z axis is taken as the principal axis. Now, if you are given a molecule, how will you decide that what type of axis actually exists in that particular molecule, or through which one you can rotate the molecule, as we have x, y, and z axis. First try it with this one. If we rotate a molecule along x-axis, we get an inverted structure. So both of these structures are not superimposable. You can say not a mirror image of each other. Okay, now this y-axis toward us, this x-axis is on horizontal plane, this is a vertical. Now rotate the same molecule by C2 axis along the z axis. You can see when you rotate this molecule, this hydrogen will come over here, this hydrogen will be shifted over here. Okay, so you get exactly the same structure. Okay, now choose that axis which gave you the identical structure after performing some operation. In case of hydrogen peroxide, a trans molecule. Now, how will you decide which type of axis exists in this molecule? C2 axis? No, structure not the same. C2Z axis? No, structure is not the same. And along y-axis, if you perform C2 operation, we get the exact structure. Forget about the numbering. Numbering are just given to simplify the operation, or just to show you that operation has been performed. Okay, so this molecule possess C2 operation along C2 operation over here, C2 operation along y axis. Okay, mirror plane. We can also explain a mirror plane over here. We will explain it later on as well. Now, how will you decide that what type of plane exists in such type of molecule? Okay, a plane along x, y, z, no identical structure. Okay, a plane along x, z, it means that it has cut this. If you apply a sigma xz plane, it will cut this hydrogen, this oxygen to equal parts, this oxygen. Okay, this hydrogen will be cut into equal pieces, and this one as well. So you get an identical structure. Forget about the numbering. Okay, so these two structures are superimposable on each other. Okay, there are two types of planes. One is vertical and one is horizontal. This plane is along the principal axis, you can say. No, this axis is perpendicular to the principal axis, means sigma h. Okay, so sigma h exists over here. That's why its point group is C2. C2 means 180 degree rotation, and h means that sigma h exists over here. As you know, this y is toward us. If it is toward us and we just pass a line, a plane vertically, then this y plane will be perpendicular to the x sigma xz, to the xz plane. So it is actually sigma h. Okay, so sigma h is always perpendicular to the principal axis. Now we take an example of ammonia, which is having a pyramidal structure. There are three equivalent proton. This one, this one proton, this one are all equivalent. But we have just labeled it 1, 2, and 3 for simplicity. Okay, by passing a C3 axis over here, okay, rotated by C31. So there are 3 atoms. So definitely these are 3 are equivalent, and definitely C3 operation will take place if there had been 4 atoms, equivalent atoms, then C4 operation would takes place over here. So C3 means 120 degree rotation. So applies first C31, you will get this structure. A and B are equivalent but not identical. Again apply C3 operation, it will become C32, means 120. Here 120 plus 120, it will become 240. You will get another orientation. These are not identical but equivalent. Again perform C3 operation, you will get an identical structure. Now A and D are identical. They can be superimposed on each other, means these two are superimposable on each other, right? Okay, now there are two axes of rotation, C2 and C3. So which one is the principal axis? Of course C3, because it is of a higher order. This one is of a higher order. This one is the principal axis of a rotation. C2 mean you have just flip the molecule. By flicking the molecule, like if you perform C2 from here, this atom will come over here, okay, and this will come over here, just like exchange of atoms, right? Now you can also rotate this molecule this way. Okay, then what will happen? This atom will come over here, and this will come over here. Okay, you can also rotate this molecule by this by applying this C2 operation. Now this F1 will come over here, and this F2 will come over here. Now if we perform C3 operation, this will flip into another orientation. You can say by C3 operation, imagine this, it is a planar molecule. Okay, and you just pass C3 like just making a hole in this boron molecule and rotate it. When you rotate it by 120, this F3 will come over here, F1 will come over here, and F2 will come over here. Imagine that all atoms are same, the numbering are given just for simplicity. Now plane of symmetry. By plane symmetry, what we mean by plane symmetry? Just as we have discussed earlier, that symmetry means an operation which bisects an object or molecule into equal wholes. Here, plane of symmetry also means a plane that bisects a molecule into equal wholes. Just like you put an object in front of a mirror, and you can see the image of that object in a mirror. Okay, I mean it has reflected the mirror or the images. So this is called plane. Okay, so we have different types of plane like dihedral plane, vertical plane, horizontal plane. There's some other operation as well, like point of symmetry or center of inversion, axis of symmetry, or improper axis of rotation. This one is dihedral plane and vertical plane. Horizontal plane is a plane that bisects. You consider it perpendicular to the principal axis. So here by horizontal plane and vertical plane we mean, in case of horizontal plane, it is a plane which is perpendicular to the principal axis. Like you have principal axis, suppose this one, if it is C, like C2, okay, and you just put a plane over here or bisect a molecule, then this plane is called horizontal plane or sigma h. In other case, if you have principal axis like C2 or C4 or C3 in even, and you just place a plane over here, or you just cut this C2 principal axis with a plane. This will be called a vertical plane, sigma v. In water molecule, a mirror plane, sigma v. You can just like cut this molecule by this plane in this fashion. It will cut the oxygen molecule into equal parts, hydrogen and hydrogen. Okay. Another plane, just pause this plane in this fashion. It will bisect, it will cut this oxygen into equal holes. Now On right side, on left side, half oxygen and complete hydrogen. On right side, half oxygen and complete hydrogen. This can also be taken as just like place a plane in front of this water molecule. It will reflect this water molecule. So sigma V is present. Now if we talk about sigma h we know that it is always perpendicular to the principal axis. F was plane perpendicular to the principal axis. If it cut this oxygen atom, this hydrogen will be reflected upward. Okay, and this will be upward in some part of this oxygen, so it will not be a mirror image of each other. So sigma h is absent in this molecule. Now here it is a better picture of excuse me, C4 C2. C4, if we apply C4 operation, means 90 degree. This hydrogen will be like this one will be shifted. F4 will come over here, means 90 degree rotation. This molecule has been rotated through a 90 degree. This atom will come over here. This one over here. This one over here. And this atom will, you can say, replace just like to replace this place of F4. Okay, now performing C2 operation 180, you get this structure, right? 80 means 180 rotation. This atom will come over here. This will come over here. Likewise, this one will be placed over here, and this one will occupy a position of F2. Okay. Right. Excuse me. Now perform sigma h horizontal plane. It will be like cutting this molecule in this fashion. Cutting this molecule in this fashion. Okay, we'll cut these 4 fluorines as well as this xenon atom. Okay, it means sigma h is perpendicular to principal axis. Excuse me. Sigma v1. Here two sigma v exist. First one, if we take this one, mean cut this, like cut these two, place a plane over here. This one will, you can say, this one will reflect this one. Okay, sigma v. This one will reflect this one, okay, and this one will reflect to this one, okay. Now if we put another plane like in this direction, we get to sigma 2. Exact rotation is the first one, okay. Dihedral plane. Di mean two hedral mean like side or planes. So dihedral plane is a plane that bisect two C2 axes. Here this C2, here is this C2. So this will be a dihedral plane, and the angle between the two planes I will be called as a dihedral angle. Now, how many sigma d mean dihedral plane exist? Okay, one passing. Well, it is just like a modified form of you can say sigma v. Sigma v is taken vertically along the principal axis. The same manner, sigma d is also taken along the principal axis. One sigma d and the second one over here. The second sigma d is just over here. So one sigma d1 cut both the f4, f1, f2, f3, and the second sigma d passes between f1, f2, f3, f4. Here another example of the dihedral plane. C2, C2, it just bisecting these two C2. Here is a better example. C2, C2, it is bisecting these two C2. Here you can also see in benzene a dihedral plane exists. Okay, so that was all about a dihedral plane. Well, if we think about water molecule, in water molecule, no dihedral plane exists. Okay, because there are not any C2 axis of rotation that can be bisected by this dihedral plane. Okay, if there is any C2 axis perpendicular to the principal axis, this is called dihedral axis. Note, a dihedral plane can also be defined as a plane that a vertical plane along the principal axis that bisect the two C2 axis. Now, center of inversion. It means if there is a molecule, that molecule may be inverted. It actually passes through the center of a molecule. If you can draw a line that passes from one atom to the other, but also pass to the center of the molecule, then we say that center of inversion exists. Like here in orbitals, often G and U labeling are used. Why? In G orbital Girardi means equally. On Girardi means unequally. Okay. F inversion is present mean in G inversion exists, why it is called Girard. Some people pronounce it as Gerard, some pronounce it as Gerard, but to the best of my satisfaction it is a Girard. Okay, now we are going to apply center of symmetry in a particular molecule. Here, trans hydrogen peroxide. If you draw a line from H2, it passes to the center of the molecule and reach a point where the same atom exists, means just like reflection of this atom. So these two atoms reflect each other. It means symmetry exists. Okay, just like exchange of atom take place. This line is called center of inversion. Okay, in water molecule, inversion is absent. In the non-tetrafluoride, you can see two inversion. You can see inversion center and two lines are passing through this center. Okay, these hydrogen replace, you can say, each other. Yet you can say these two fluorine atom exchange its position with each other. So inversion is present in such type of molecule. Okay, to present it simply or to make it more simplified, take this imaginary molecule A and A. Both are A but colored differently so that you can just see that after inversion what happened actually. Okay, so this B is exchanged with this one. Okay, over here you can see this one exchange with it, this one exchange with this one. So you find a structure with the identical orientation. Forget about the color black, say blue and red. These are just given here to differentiate the two structure in the sense of like a orientation. It's just like a double orientation, first and second. C2, here if you apply C2 on this particular molecule, okay, this will come over here and this one will come over here. Okay, same one. How you can differentiate C2 from inversion? Inversion is just like a double rotation, whereas principal axis of rotation is just like a single rotation. So here you can also differentiate C2 from inversion. Remember, sigma D is present in highly symmetrical structure, but often very rare. Okay, sigma H is present in fewer structure. It is a very small number of structures possess sigma H, and sigma V is present in most of the structure. While the order of reference is sigma D, then sigma H, and sigma V. If a structure possesses, but in some cases, if a structure possesses sigma H, sigma D, sigma V, then sigma H is preferred. Okay, the rest you can just read it. If a molecule contains odd number of atoms, the sigma we divide the object molecule into equal halves. Okay, like H2O. The sigma can be applied only once during the symmetry operation. If you apply it twice, it will give again the identity. Mean, if you apply this water molecule H1, H2, let's apply sigma V. Okay, it will give us like a structure H1, H2. If we apply the same sigma V, it will give the same structure. So sigma V is performed once in a molecule. In any sigma can be applied once. Once. Okay. Proper axis of rotation. So it is not just like a proper axis mean CN axis. It is something else. Well, it is a type of rotation where the proper rotation is followed by a mirror plane that bisecting, you can say that are perpendicular to the principal axis. If molecule possesses improper axis of rotation, the symbol that element Sn is used for it. Okay, now we come toward a molecule and try to perform it. This one. This molecule has chlorine A, chlorine B. Chlorine A, hydrogen B. Just rotate it by C2 operation. Okay, this hydrogen will come over here, and this chlorine will come over here. Likewise, this chlorine will come over here, and this will come over here. Okay, exchange of position has taken place. Now this is C2 and this is perpendicular to the C2, this plane. Okay, if you use this plane, what will happen? It will shift it over here, will be reflected over here actually. It will be reflected over here. Okay, in the same manner, this one will be reflected over here, and this one will be reflected over here. Forget about the labeling, just for simplicity, it has been assigned over here. Now you can see the same structure. The same structure, forget about it, B, A, etc. You can superimpose these two structures. So these two structures are mirror images of each other. It means this particular molecule possesses Sn in improper axis of rotation. Another molecule, apply, rotate it 90. Okay, shifting atom will take place. This is the principal axis. Sigma, it is perpendicular to the principal axis in sigma h actually. Okay, you can get the same structure, like the same orientation like first one. This one is same like this one, superimposable on each other. Just forget about the number H3, H4, H4, H3, H2, H1, sand, it is in sand just for simplicity. Okay. We come to water molecule. We have started our discussion with water. Now we are going to end our discussion with water molecule. CO2 this will come over here, this will come over here like H2 H3. Okay, now this will become H3 and this will become H2. Now just take sigma H. It is also sigma H. Reflection? No. The same molecule, you can see the same atoms are not present in such a fashion that can be superimposed on this one. So structure third is not superimposable on structure one. So you can say that SN operation do not exist in water molecule. Thank you very much. Please subscribe, share and like my channel. Allah Hafiz.